given. So I'll come back to this in detail, but the leading classifier at the time called that a Panda with 57% confidence and that a gibbon with 99% confidence. That's not good. So why are these things, and I'm not bringing this up, right, because some adversary is going to take our telescope image and add some noise to it to make a galaxy look like a gibbon. You know, that's not going to happen. But if we don't understand why these things are fragile, we should be concerned, right? So one cause of fragility is overfitting, I assert. If you ask me to prove it, I'll prove it by repeated assertion. These are just sophisticated fitting functions again. And I want to be careful saying that, right? That's kind of like saying astronomy is just physics. There are emergent phenomena in astronomy that you would not have predicted if you just know physics, right? So there's more to it than that. There's such sophisticated fitting functions, there are emergent behaviors that come out of them that we wouldn't have guessed. But at the end of the day, they're fitting functions. And so you have the same problems you usually have. Does my fitting function have enough freedom to represent the distribution I want to represent? Does it have too much, so it's overfit? And then it'll fit the training data well, but fail to generalize. You know, exactly the same problems we always have. And you know, one of the reasons I think this is so important is the space of all possible real images is a low dimension manifold in the space of all possible images, right? If I take a picture of this room and then permute the pixels, you can tell it's not the original pixel. Yeah, I mean, it's the same distribution of brightnesses in pixels, but the correlations of the neighboring pixels are something that makes it look real. Big swatches of the same color, sharp edges. You know, there are lots of things that real images have in common. And so you have this low dimension manifold. I mean, low means only 10,000 dimensions. You have this lower dimension manifold in this million dimensional space, and all your training data is on it. And if you then test your neural nets on examples that are on that same manifold, it seems to work pretty well. But it fails to generalize. As soon as you move off the training manifold, you know, I think the technical term is all hell breaks loose. And so just, you know, the 1D version of this, very simply, is imagine that I've got some function, that's the black line, that's my true function. I've got some noisy samples from it that are the green dots. And I've maybe got a validation training set that's not drawn from the same domain. Similar noise and everything, but it's a restricted domain, those are the black dots. And so I'm going to fit a fitting function, a polynomial, for example. That polynomial is too low order. That one's about right. That one's too high order. So how do you know? Well, if your fitting function, if you're underfit, the error on the training data is, you know, larger than you might expect it to be given the noise. If you fit it well, then things are fine. If you are overfit, the error on the training data collapses down towards 0, but the error on the validation data gets worse, right? Because you're overfitting, you're not generalizing to the validation data. So the overfitting is obvious in this case because the fit does much better on the training data than the validation data. Now, if you distribute that training data a little differently, right, so it's mostly where the validation data is, but has some outliers here, you can get fitting functions like this. Okay, so actually here it's not obvious at all that there's any difference between the good fit and the overfitting case. So the reason I'm going through this is people will often talk about whether their neural net is overfit or not. That is not the question. It is probably always overfit in some dimension or in some region of parameter space, and well fit in others. And the problem is, we tend to train and use them where they're well fit, but then we'll get an input that's away from that domain, and you know, chaos ensues. Yes?
I don't see, the main thing, I don't see the difference between this and how our brain works, because our brain is like the same idea, it works by training. Maybe like the mechanism is different, but we also use, the brain works by training data sets, and then we make good predictions. We won't be fooled by adding some noise to a Panda and say it's a gibbon. So I don't see why for the neural net it's such a big problem, and for us it's so trivial.
Yeah, I mean, our brains must have many layers of sophistication above what you get out of repeated compositions of functions that are mere matrix multiplications piped through a nonlinear function. Right? I mean, that's a very simple model, actually. Yes?
I mean, in contrast to that, I mean, we do get fooled by patterns that may not exist very easily.
Yeah.
So, just, often when I think about fitting, I'm thinking about a merit function, and an essential part of that are uncertainties and error bars. But here, there's no error bars, or just, how are you accounting for uncertainties in your measurement?
Right, so I knew that would come up sooner or later. There are different kinds of uncertainties, right? There's the, each of the training images has some noise in it. That's not an issue for the Panda. It is an issue for astronomers, right? We're in the low signal noise limit often. Then there's the noise that comes from the fact that you want kind of 10 to the million training samples, and you have fewer than that. Right? The training samples do not fully specify this PDF in the high dimension space, not even close. So there will be some noise due to that. Then there's noise due to the fact that your optimizer didn't optimize. You're looking for an optimum in some space of 100 million neural net parameters. It's very unlikely that you found the true optimum. Right? So there are a lot of issues here, a lot of places noise can come from.
I guess what I'm saying is, in that previous example, error bars provided an easy way to distinguish between overfitting. Because you want the minimum number of parameters,
Right.
at which point you're cut. There's nothing left to explain in the data.
Right, so we don't really have that here, but I guess my point is that's often not the issue anyway. The main issue is that you've trained on some manifold and then you're trying to use it off that manifold.
No, I get that. I just
And that could be far more disastrous. So a lot of work has been done. I don't have any slides on this, but a lot of work has been done, on making this more scientist friendly. So you can, instead of training to some fixed set of neural net parameters, you can keep a distribution of the parameters, right? Some Bayesian distribution of neural nets. So you don't have one neural net, you have many, and then you can evaluate all of them and see what the distribution of the outputs look like. That's a CPU intensive way to do it. Anyway, I don't know too much about that, but I know people are concerned about it. And it depends in what way you actually want to phrase your problem. I mean, we are learning this really complex PDF, and then often we just boil it down with this very simplifying function at the end to turn it into class labels. But this is a great way of modeling high dimension PDFs, and that is what we want for a lot of our problems. We just want the PDF. And so that would mean using these functions a little differently than they're normally used. But I think it's all in there. I think it's all possible.
Sorry, related to that. Can't you deal with this statistical noise, I guess you're talking about, in terms of your training function? So you can simulate that and feed different training functions and see what effects it will.
You can, and you can do things like have training samples with different realizations of noise, and when you put in your inputs, you can input them with different realization of noise and see how much the answer changes. You can do all these things. They've been shown not to work terribly well. There should be a better way of getting at the heart of that problem. So one thing I wanted to highlight, I showed my crumpled up tinfoil image and kind of went past it, but there are these boundaries in this high dimension space, and so you have to imagine 10,000 dimension tinfoil in a million dimension space crumpled up quite densely, and that tinfoil represents the boundary between Panda and other classes, say. And so somehow, when we're attacking something like that, we're looking at this Panda and we're saying, okay, where's the nearest boundary to something that's wrong? Let's go over there. And it's an image that's pretty close in pixel space, right? It looks like a Panda to us. And it's in general, far too close for comfort. And so I'm going to take you through some what are called adversarial examples that demonstrate that in more detail. Okay, so what's actually going on here, remember I talked about this loss function j. It's a function of the neural net parameters theta, and then inputs and outputs, x and y. So now we're going to take the gradient of j with respect to x. So we've already trained a neural net. We're just asking, as we change the input image x, how do we change the loss function? And so we're going to start at some arbitrary place in the image space that happens to be an image of a panda. And then we're going to evaluate this gradient and just take the sign of it. Just, is it plus or minus 1? And multiply it by some small number. Okay, so we have this thing that looks to us like noise. And we add that adversarial noise to the panda. Looks exactly the same. And now to give it at high confidence. Higher confidence than the right answer was. So this is cheating a little bit. This kind of noise pattern would never occur by random chance, right? This is just preposterously unlikely. But the fact that it exists, you know, and then you can do this in general. You can start from any image, and you can do this on any classifier, and you can always get this kind of thing. This is disturbing because it means the boundary to the next class is kind of arbitrarily close. You can start anywhere in image space, actually. So these are random points in image space. They look like just random noise. This is the CFAR 10 data set, which is one of the commonly used in machine vision. And so we're going to take each of these 100 images and take one gradient step towards class airplane. Now all of the yellow boxed images are airplane. So why did they use airplane rather than one of the other classes? This was actually the hardest case. For some of the classes, it worked 100% of the time.